I want to give you a crash course on the sort of multivariate analysis which we need to use. So run through the basics from multivariate probability densities, joint densities, and through covariances, just to prepare you a little bit for this stat545.1-020 lecture. So if y is a random variable with a continuous density or probability density function f, what that means is that f has to satisfy certain conditions. We have to have f of y greater than or equal to 0 for all y, for all real valued y, and we have to have the integral f of y dy equal to 1. And here it's understood that we're integrating over the whole real line. For a pair y1, y2, they have a joint probability density function f if f of y1, y2 is greater than or equal to 0, and the double integral f of y1, y2 dy1 dy2 is equal to 1. And of course, in this first case, this is just the criterion for f to be a density. We also need the probability that y is in a set A is equal to the integral over the set A of f of y dy for those a's where this can be integrated. And here we have a corresponding criterion, the double integral over the set A, f of y1, y2, dy1, dy2 is equal to the probability that the pair y1, y2 is in the subset A of the plane. Now, and the same thing happens to n dimensions, in which case you simply have an n-dimensional integral. Now, y1 and y2 with joint probability density function f are independent if the density of the combination, the joint density, is equal to the density of y1 at the point y1 times the density of y2 at the point y2. And when this happens, the only way this can occur is if this is the PDF of y2 and this is the probability density function of y1. Now, and they're not always independent. There are lots of examples where of random variables which are not independent, and we'll run into a whole bunch of those. And similarly, if a vector random variable y1 through yn, this with PDF f of y, or f of y, if you like, these are independent if and only if you can write f of y, vector y, is f of y1, f1 of y1, if you like, f2 of y2, times and so forth, all the way up to fn of yn. And these densities may be different, right? For example, if you're talking about the probability densities for y's in regression, these densities are all different because they have different means. And now, what I want to add to this is for two variables. If y1, y2 have joint PDF f, function of y1 and y2, then we define the covariance between y1 and y2 to be defined as to be the expected value of y1 minus the mean of y1 times y2 minus the mean of y2, and to be specific, where mu1 is the expected value of y1. So this is simply this can be computed either as the integral of y1 times fy1 of y1 dy1, or the double integral of y1 times f of y1 y2 dy1 dy2, and mu2 is the expected value of y2, and the covariance can be computed with the expected value, the double integral of of y1 minus mu1 times y2 minus mu2 times f of y1 y2 times, or dy1 dy2, if this exists. And that applies in all cases. And it's important to notice here that if y1 and y2 are independent random variables, then this density factors into the product of the two densities, and then the entire integral factors into the product of two integrals. And they're both zero, because the integral of y1 minus mu1 fy1 of y1 dy1 is just the expected value of y1 minus mu1, which is equal to 0. So, and that's important. It's also important to realize that you can use these basic definitions to compute the covariances and expected values and so forth, and variances of any linear combination of y's that you like. And you should note here that the covariance of a random variable with itself is simply equal to the variance of that random variable. And that's enough on this. This should give you the sort of background that you need to complete the, or to read the text in 545.1, the whole thing. And it should give you the background needed to look at the video for the corresponding section. Thank you.